喂，喂，Hello，喂，喂，
你大概会累个几秒？有了吗？就现在的设定反而跟昨天不一样有还是没有？就是因为跟昨天设定不一样啊。画面是顿的，不顺的吗？
同学在后面3排不要坐，你在后面3排不要坐，听到我的动作。
一如你看一下影像好了。画面是顺的还是顿的？顿一下的吗？那就不对啊，那就设定不行。我切回昨天的设定哦。好，再看一下
后面3排不要坐。
再看一下这一次的设定。现在是有讯号还是没有讯号？
有讯号。可以啊。
可以了吗？所以刚刚没讯号不是我这里的问题啊，因为我刚刚现在直接切设定，你那边也没有断讯啊。那就维持这样喽。水平横线解决不了，对不对？
要，你先去站下去。站人没有水平。
喂，喂，喂喂喂，喂，test test，喂喂喂，Hello，喂喂喂，Hello，你好，喂，Hello，喂，喂喂喂，Hello。对。
那这样搞。
等下跟你讲这一台要怎么操作。你先过来这里。这台你有使用过吗？这台？没有。好，就是它监听的话，你一定要带，从头带到尾，一定要带着。然后这台比较特别的是，它没有像旁边这一台的那个声音好有按键可以按，它没有，所以它完全要靠这个转。所以你转的话，记得水平通常我不会锁很紧，但垂直一定要锁紧的原因是因为如果你放手的话，它会往前掉。那你要任何要移动的时候，你水平就先松，不用松到很重，反正只要你就稍微把它解开，然后手开始转。往右边是顺时针的话是那个录音，然后粗的这个不是哦，这个对焦的，就是顺时针跟逆时针。但你可能要练习，比如说我今天要顺时针，我今天要顺时针，我这样转可能会不够，会卡到我的手。所以你习惯就是让自己手的弧度大一点，然后再转它，这样你的音会一次到位。好。那今天的，因为他昨天有来预演，他大概就是他会习惯在前面走来走去。那因为我们要带布幕，因为我们要直播出去到网络上，所以必须要讲者跟布幕一起连接。那画面可能就是维持这样子的。不用拍到第一排，不用拍到第一排的椅子区。那第一排的也许会坐人，会拍到头也没关系，但就不用拍到椅子。大概就是它会左右移动的话，大概就在这一区，然后就大概稍微偏这一侧，它可能走到这边来会偏这一侧，然后走到这边来的话，你就偏这一侧，然后尽量画面是慢慢的带就好。对，画面慢慢的带就好。然后还有什么要知道？这3个现在有反白，有状态就是因为他们是在手动的状态，所以这个前面这个按键按下去，手动的钮按下去，它现在是属于自动，好，但我要把它变成，因为现在我觉得有点暗，我想要变成自动的手动的话，我就按一下，它会3个反白，那你旁边这个地方用调整的，调亮，对。调它的，这算它的增益值，有点像跟 ISO 的 ISO 值这样。往下数字越大的话，它就会越亮，但相对它的噪点会比较多，所以应该是不用调到这么亮，因为它的 PowerPoint 可能会曝掉。所以就稍微大概看一下你的画面，就是人清楚，然后 PowerPoint 不要曝掉。它昨天蛮多底部是白色底的。所以比较小心一点，不能扑掉。OK， 所以就大概在这边维持。那个同学，你会从头到尾先看网络画面吗？
那个会有。
会，是昨天那位外国人。
需要怎么样？我可以再找一位。
就是可能因为我们这边看到的画面不代表你那边看到的画面是 OK 的。我怕说我们这边看起来布幕没有曝掉，可是你那边网络上看起来是曝掉的，所以你可能要告诉我们，我们再把它调暗一点。
那我会再请，因为我这边只带一台电脑。没有，我这边有个看。这台电脑这台电脑应该也可以看。
好，那
他在后面发问时间的时候，他必须跟那边去，他们在发问。
是哦，那我请我们组长看好了。
或者说我再请一个同学。没关系，我也要在，因为我要确认。
网络都正常。
好，还有我问一下，今天是比较暗。
那前面灯好像还没有开。
前面灯会不会再打？因为我是看降噪的时候
偏暗，对不对？
对啊。
所以你看他那边可能，我这边看起来，我们觉得这边看起来 OK， 他那边会偏暗，所以你就是稍微再亮一点，比你想看到的画面再亮一点。好，所以成这样的画面 OK 吗？我说亮度啦。因为我刚刚有稍微把曝光调大 ，OK 吗？这大概是27，好，27左右。就 就是如果你这边看起来有点铺掉，也许它那边是正常的。好，所以大概这样。然后同步的话要录影，就是这个键要记得按下去，或者是旁边这个键。
好，
这个键，红色的键。
好，
录影键。那到时候2台我会同步录，这样。我先把蓝牙关掉，然后等一下等一下我会帮那个讲解别，然后我别上去的时候，你就要先帮我监听他那边讲的，那边是什么。因为我怕他那边万一突然讲话很小声的话。
是1点整看什么？
我看样子应该是1点10分。好，我先调整一下。然后你先练习一下镜头，然后其他都不要动到。尤其这条线不要动到，因为这条线主要在接直播的。今天没有什么，好像没有听到什么杂讯的声音，还是你现在没有转很大声？你现在没有转很大声吗？
对，今天、昨天，
现在我把它总音量
压低了。
就拉低，
对。
你去旁边听一下，是不是还有噗呲噗呲噗呲的声音？还是有嘛，只是这边听比较不清楚而已。
这个听得应该听得到的，我刚刚听也没听到。
就是要坐旁边才听得到。
对啊，我刚刚中间
应该是听得到。
对。
还需要再大声？
应该不用，这样可以了。
那刚刚你有帮？
你这个的蓝牙在哪里？
在里面，跟那个电池放一起。
对。
然后我前面会放第2颗蓝牙麦克风，是预备录音用的。讲者会别我手上这个，我等一下再帮他别。好，你赶快去。好，你说让他讲话是不是？你就 test 1、2、3、4，你去前面。你就当心走来走去，我画面会带你。
哦，好。喂喂喂 ，test one，test two。 Test 3, Test 4, Test 5. 1 2 3 1 2 3 Test 1 Test 2 Test 3 Test 4 Test 5 1 2 3 1 2 3 Test 1 Test 2 Test 3 Test 4 Test 5 1 2 3 1 2 3，这样可以了吗？Test 1, Test 2, Test 3, Test 4, Test 5. Test 1, Test 2, Test 3, Test 4, Test 5, Test 7, Test 8, Test 1, Test 2, Test 3, Test 4, Test 5, Test 7, Test 8, Test 9, Test 1, Test 2.
Amel will connect with you on this speech. Yeah. Okay. And okay, thank you. Okay, goodbye.
等一下那个，
那个等下
你 OK 的吗？
你们等一下流程是怎么样？因为等一下如果院长颁奖的时候，我们南亚可能要让他们别上，要不然因为
前面院长会致辞的嘞。
是。对，前面院长会。
可以先跟我说会有几个人致辞吗？
稍等一下，我看一下。
因为如果你要致辞清楚的话，可能蓝牙还是要别在致辞那个人身上，那必须我们只有一组蓝牙，就必须要更换。
一开始这里最近那个
是，一开始是。
等一下哦，Wednesday。他没有写那个 round down。
是哦，那个不是吗？
他早上的。
是早上，这边
哦，
这个吧。一开始是老师，再是院长，再
老师是哪一位老师？
张老师。
昨天来的那一位吗？
对，然后再来是院长，然后院长讲完之后，就换那个 speaker
主要的好。
speaker 讲完之后，老师再说上去再做 ending，这应该是这样。
开场的部分是
开场部分。
开场2个，然后讲者，
然后
再回老师，还是回院长。
If you have any， 一开始是老师，再来是院长，然后接下来这2开场白完之后，院长会请讲者上台，然后讲者讲完之后呢，老师会上台做结束。也是张老师吗？对。4位。所以一开始应该是张老师，然后院长可能就
再帮他别一下，
叫帮他别，然后院长讲完之后，老师下来把老师的麦克风
对，必须要有一位帮老师做别的动作。
那个，好像，来，就是那个麦克风。 不然呢？
穿拖鞋啊？
啊，那不然我找，不然我找一个穿布鞋的。等一下，我找一个穿布鞋的。立成，来，快点，快点。啊，不用，立成来，立成来，快。
女生
看是女生和男生都可以，还是要女生？
我看你们。
立成啊，立成。靠北，立成是中间打人哦。来，立成。那个。
等一下，就是因为我们这个必须要别在主讲的人身上，可是因为前面会有2位致辞的，那可能要你帮他们别在身上 ，OK 吗？第一位会是张老师完之后是院长，然后院长完之后是今天的日本的那位讲者，结束了他讲完之后会再回到张老师。那这个因为我们是主收音那个直播那边的主要声音，所以必须要谁讲话就要别在谁身上。那你可以可能就坐在第一排，帮他们及时做这样的更换。
好，没问题。
对，然后从头到尾电源都不会关。
好。
好，所以那像讲者他昨天有穿那个像衬衫像这种的，就帮他别在前面，这个压下去，然后别在前面的。
就讲再讲。
对，万一。
如果穿没有口袋的话，
如果没有口袋的，应该不太可能穿进去。
但是有些衬衫没有口袋。
没有假设没有口袋，你就帮他别在这里。
好，
可以好，就大概是这样。等一下我会帮你看一下，就是他们的。啊，我先把蓝牙关掉了，现在好。那我等一下再给你。
好，没问题。
谢谢。 有吗？那东西交给你了。哦，那电源它是打开的，先别你身上，才不会不见。
各位同学，这个演讲会在 IG 会议上直播，我们会我拿一下，大家结束了才Surface 尽量先往中间做，不然中间是空的。
已经上线了吗？
是打开的，打开的。
放，这边可以，一定要这么要近吗？
对，要这样子。
要这么近。
稍微有一点。
啊。
那如果想要在那个网络上秀到哪里的话，可以准备好题目，等下可以发问。那个同学，一起立，左边面啊，中间对，我们中间先做，好不好？先往中间做，让中间先做满，等下后面出去还会有人。那个同学先往前面，好不好？前面这边还有2排。那我们1点半开始，各位同学配合一下。请后面的同学往前坐。
等一下，那个问问题你们都安排好了吗？
有那个易伟跟那个学妹他们会负责递麦克风，然后
要问问题呢？
对，那如果中间这边就老师就直接
对，阿蛋缴 email 呢？
email 的话有阿米跟那个 Sina， 阿米负责跟他用 Skype 跟 mail check， 然后 Sina 可能要么就是 Sina 方案，要么就是阿米方案。
OK， 就他们去轮。After I introduce you and the Tim Sun here, I will pass my microphone to you. So you always two microphones. One is the hand in your hand, and one is the put on your clothes.
This side.
Yeah, but there's only two. So I take one and Tim Sun take two.
Okay.
After my introduce. Yeah.
The other is the wrong.
Yeah.
Another one.
Yeah. You get two microphones. Yeah. I will pass it to you after I finish my talk.
I see.
Yeah. Okay. 好，欢迎各位同学来听我们本学期最后一场演讲。我们很荣幸邀请到日本东京大学的Professor Akira Hirose， 他是东京大学电机系的教授。同学将来假如希望去那边留学的话，今天的演讲更应该要发问问题你才有那个获取东京大学那个的就学入门票。我老是开玩笑了。今天我们很荣幸因为应该是全台湾第一个学校，我们 iChikoI.TV 会来现场直播，所以意思就是说，各位同学为了让我们学校的 这个 reputation 啊可以好一点啊，是不是同学啊？后来同学都可以麻烦往前坐，好，因为等一下我们的镜头啊是全世界即时广播，然后你的问题呢都全世界的观众都可以听得到，好，所以我们希望同学是不是后面3排同学可不可以往前坐？我们后面3排不要坐，同学可以吗？好，这个老师希望说，我们可以帮忙，我们后面3排同学可以往前坐，可以吗？好，后面的3排同学可以往前坐。好，那个后面同学 ，C B 啊，对，那个后面这一排同学，这个前面都很空啊。好，你有可能就是未来东京大学的博士生哦。后来同学可以麻烦往前坐，后面3排同学可以麻烦不要坐。好，往前坐，谢谢。好，我们还有10分钟就开播哦，请同学哦可以，把你的手机务必一定要关掉哦，因为这个现场直播怕会把我们的这个无线传播的信号干扰。好，麻烦你把手机关掉。好，我们后面3排同学不要坐了，可不可以麻烦同学往前坐？好，老师那个拜托各位可不可以往前坐？好，这边都空的，前面都是空的。后面3排同学可以吗？往前坐。好，拜托一下，需要老师上去拜托吗？好，前面有位置。好，再10分钟哦，我们要把握时间，好不好？好，同学那个为学校荣誉，我们是全台湾第一个上 iQPOE.TV 的学校。后面3排同学，都没有动啊。好，你假如不做的话就没位置了。好，谢谢。这边也可以坐。然后你坐前排，停下来可以问一个问题，我相信哦，那个 Professor Akira Hirose 哦会优先考虑你当他们的研究生。那个同学这边前面有，可以麻烦。前面。好，我们今天的演讲题目哦，等一下哈，我们会秀一下我们今天演讲的题目哦，是主 主要那个着重在我们的现在最夯的那个机器学习那个类神经网络也是所谓的深度学习这个 topic 是现在全世界炒得很热不管是哪个应用今天 Professor Akira Hirose 他会利用这个机会介绍他的专业领域也就是在做这个雷达的影像的应用我想这个是机会难得。在这个讲座里面呢，他有讲到一个比较特别的，就叫复数的范围的neural net 的类神经网络这复数同学知道，那类神经网络里面的高维的这个变数里面呢，这个复数变数这个复变数呢，是一个很应用很广的一个数学模型在这个模型之下 ，Akira Hirose Professor 他有他独到的见解他并且已经是2本 textbook 的作者所以我们想今天的演讲，希望同学或许真的不是你的领域，但你可以尝试听听看到底 Akira Hirose Professor Akira Hirose 他带给我们哪些很好的 idea。不过我们也刚刚我们孙院长有正式邀请Professor Akira Hirose 给我们会来担任我们的International Chair Professor 他已经欣然答应我们可能在下个学期会开Professor Akira Hirose 会开一门课我们同学也希望同学可以热烈修他的课。不过要毕业的同学也很欢迎你们继续留下来念 PhD 一定也有机会可以修到他的课我们已经有那个孙院长我们下任院长都 promise 黄院长都 promise 就是我们会 maintain 这个关系，然后将来我们会希望跟东京大学有很多的 project 可以合作。OK。同学可以想一下，等一下你可以问什么问题？你希望你的问题你的影像可不可以广播到全世界这是个难得的机会你可以等一下专心听一下Professor Hirose 他的演讲老师主持呢，我们的研究讨论从来没有这么紧张过。我们现在倒数计时，Final Countdown 很像快过年我们接下去还剩5分钟同学，我们可不可以开始倒数计时？Yeah, we have a final countdown for celebrate the new year event. Okay. You can put your slide first here. Yes. But no signal here.
Yeah.
Switch to.还有4分钟，同学先花这4分钟，先把第一页这个title 你有没有看懂？他在讲什么？ 好，还剩3分钟，不到100秒，我要说180秒，我们倒数计时啊，制造紧张、恐怖、悬疑的气氛。Are you okay? Yeah. Two minutes more. 我们冷气好像不够凉哦，那个老师一直在流汗，我想同学等一下可能也会那个慢慢进入梦乡嘛，太好睡了。我们可不可以请我们工作同学可不可以把冷气开强一点？
提到有那个 IEEE.TV 可以提到有关IEEE.TV 有现场有在，就等一下。
好，剩60秒。Okay. Good afternoon, Professor Akira Hirose, and Tim Sun, Professor Huang, Professor Tan, and all of the audience, both on site and online, special for IEEE.TV. Welcome. I'm Scott Yang Lang Zhang. On behalf of Taipei Chapter Chair of IEEE Geoscience and Remote Sensing, it's our honor to invite Professor Akira Hirose to deliver an IEEE GIS distinguished lecture talk at Taipei Tech. Now, let's welcome our team, the College of Electrical Engineer and Computer Science, Taipei Tech, Professor Sun Zhuoxun, to deliver an opening remark. Welcome.
Thank you, Mark. Thank you very much, Scott. Good afternoon, ladies and gentlemen. I'm Jason, as you just Scott introduced. I'm now the Dean of the EECS of Taipei Tech. I would like to express our sincere welcome and thanks for Professor Akira Hirose's the distinguished talk will come in here. And then the topics of the today is the advanced neural adaptive processing in the interferometric and polarimetric radar image. As you may know that Professor Akira Hirose is now working with the University of Tokyo, Department of Electrical Engineering and Information System. He is also the fellow of the IEEE, got a lot of the prize and award, and a senior member of the IEICE and the president of the Japanese Neural Network Society. Dr. Hirose, he received the Neural's Journal-Based Paper Award, Excellent Service Award, and the Outstanding Research Award. Just awesome, unbelievable. Very, very, I think, performs quite excellent scholars, such as IEICE Electronic Society Outstanding Achievement Award, IEEE Geoscience and Remote Sensing Society Distinguished Lecturers Honors. Okay, so I think it's quite a great honors for us to invite Dr. Hirosei's talk. Let's give him a big hand and applause. Welcome, Hirosei's talk. Thank you, thank you.
Thank you very much, Professor Sun and Professor Chan and everyone, professors at Taipei Tech. And most of all, I would like to thank all the volunteer students to have set up this wireless and online systems. Thank you very much. Okay, I start. Well, in this presentation, I would like to concentrate upon complex valued neural networks. And first, my motivation, and then what is complex number? Many of you will make a smile, I think. That is the first one. And then, what is the merit and what is the origin? And then we go to an example of applications. I will pick up a filtering process in INSAR, interferometric synthetic aperture radar systems. And the summary. Okay, first, my motivation. Can you see? Well, in the geoscience and remote sensing society field, we often want to observe the Earth from satellite or airborne radar systems to extract the geographical information or vegetation information and so on. And in this process, we want to develop very useful adaptive systems because the data is often distorted and includes much noise. So it is very difficult to understand the raw data directly. And in this situation, we transmit electromagnetic wave and we observe the scattered wave, scattered at the Earth's surface or sometimes underground. Then, this is the active imaging system, very different from normal camera or normal videos. And we can use the phase and polarization information. So then, we have the possibility to develop a very special neural network which is sensitive to phase and polarization. Well, the detail is given in my recent book, for example, and this is the one. I would like to give this one to Professor Chan as a small gift. Okay. Okay, this is another situation. We want to visualize anti-personnel landmines, small bomb. And this is very difficult because it is made of plastics, which includes only a small portion of metal. So very difficult to find it with the metal detectors. And the diameter is about, in this case, about 7 centimeters, and the thickness is 4 centimeters, very small. So we have developed a system, ground-penetrating radar system, to visualize this kind of small things. We developed very wide frequency range antennas to construct an antenna array, and we observe the underground. Here. Well, the frequency is stepped changed, and the range is, for example, 8 to 12 gigahertz, which is a little higher than normal ground penetrating radars. Well, then, this is the data, real data. We observe 30 centimeter by 30 centimeter ground piece. Okay, and we want to visualize a landmine. In this case, we have a single one landmine. This is the situation. 30 centimeter by 30 centimeter ground piece. Okay? And it includes a landmine somewhere, here or here or here or here. And the first square is the obtained data obtained for 8 gigahertz frequency. The second one, 8.1 gigahertz, 8.2, 8.3, and so on. The frequency is changed, but it observes the same land piece. So if you find one landmine in one of the square, then you can find a landmine at the same place, here, 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 here. Okay, this is the data, raw data. And I would like to ask you to find a landmine. Please look at this data. Very hard? Do you have any idea where the landmine is?
Different image.
It can be a possible way. But please use your own brain neural network this time. Do you have any idea? Do you find it? No? Machine learning, yes. Do you have any idea? For example, in this square, you have one landmine. Here or here or here, here, here. Where? Guess it, please.
There seems to be one in the middle, right? Because I think I can see some circular curves in the middle, where like the image that you pointed should be somewhere in the middle of the 30 by 30 square.
Yes, yes, that's right, that's right. Well, could you hear? Probably this one. No? Yes. Then you can see something here once you heard the answer. Yes, that's right, that's right. Here we have a landmine, and the system gives this answer where it says this is the landmine. It is a little different from the round one, a small error. But anyway, the situation, the location is the same. And could you explain how or why you find it?
curves around an object where the gradient has these changes.
Yeah. Well, in this image, in these images, actually, this is very difficult. Was very difficult. I'm sorry that the brightness shows the power. Can you see? And the hue or the color shows the phase. And brightness is almost homogeneous, not the peak, no dark place. And the phase is very random. But the randomness is a little different here. Somewhat around, as he said. Random, but the randomness is a little different. And, well, it is very difficult to explain logically because this one is this way and so on. Instead, we can find it intuitively, not a logic, but a feeling. Well, this kind of tasks are very suitable for us, for neural networks. It is not a logic, but something else. And we want to optimize or maximize this ability of neural networks. And in this case, we used our own neural network, your own neural network. But we have electronics. So by using the electronics and the software science, we want to develop or we want to maximize the ability in that kind of neural network suitable for radar imaging. And it is possible since a neural network is not a universal, versatile black box. Instead, one neural network is very good for this task. Another one is good for this task. And in such a coherent pattern or active imaging processing, I think complex valued neural networks are very good in interferometric synthetic aperture radar systems, INSAR. And today I will not talk about it, but the quaternion neural networks are all very good to deal with polarimetric synthetic aperture radar data, POLSAR. And when we analyze the suitability of neural networks, the most important aspect is the generalization ability or generalization property. I hear that many of you are the student in computer science and electrical engineering, and sometimes mechanical engineering. So some of you are already familiar with this word, generalization. For example, when we construct a supervised learning neural network, it happens in the following way. Well, we have an input signal, and by using a neural network, we get an output signal. And we expect that the neural network will learn the teacher signals. In this case, we have 3 teacher signals. The horizontal axis shows the input data and vertical one, output data. When the neural network receives 2 as the input, then this teacher signal point shows the output should be 5. Input 4, then output 6. Input 7, then output 4. And we apply the learning dynamics, supervised learning dynamics to the neural network so that the network learns these 3 points. And the result is given here. So, okay, the errors at these 3 points became 0. This is the learning result. But what we expect is not only these 3 points, but instead, we expect this curve. So I mean that if the network receives 3 as the input, then we expect 5.7 or something as the output. If the input is 5, then the output should be 5.3. Even if the network receives an input which was not used in the learning process, we expect something meaningful. And this ability, this output generating ability is the generalization ability. So this ability corresponds to estimation or prediction. Well, this part, interpolating this curve, is a type of estimation result. This part is corresponding to prediction. If we have time here, then this is the past data. And we sometimes expect future situation. So this is a prediction. This ability is very important. Otherwise, we don't need any learning process. That is, we just make a lookup table. Input 2, output 5, input 4, output 6, and so on. Then we make this table in memory, normal memory, and then that's all. We don't need any learning process. If this table is fed with 2, then it can make an output 5. So this is very general in logic circuits or logic processing, or in other words, von Neumann type processing. When we construct a CPU, normal CPU, we make this kind of lookup table, or more generally, truth table. You learn truth table in the lecture at the university. And then it can be interpreted into a logic circuit, and CPU is made. It's okay. There is no learning process, but you have to learn how to make that truth table. That's all. And making this curve is very important. If we have another point of teacher signal, then the curve may be different, not only at this point, but also this way. Maybe. So the curve is determined in total, not very locally, but as a whole. Okay, this is the introduction. We move to the next part. What is complex number? Everyone uses complex number. Okay, it has a very long history, almost 500 years. For example, in European countries, Cardano is said to be the first person who considered the negative number root in his solving quadratic cubic equations. Euler, you know, everyone knows. Euler's formula is represented in this way, cosine and sine. And he used this relationship to represent a point on the two-dimension, plane. This point can be explained or represented by this way. So this is very geometric, not arithmetic. And it is very interesting that he says it is clear that the square roots of negative numbers cannot be reckoned among the possible numbers. They are impossible, imaginary, fancied. About 300 years ago, Gauss was full possession of the geometric theory, and he proposed another one concerning the name of numbers. Let's call positive unity plus 1, positive unity as direct unity, negative unity as inverse unity, and root minus 1 be lateral unity. Then the number of this negative root is not imaginary, not impossible, but a real number. He believed in the imaginary number or complex number. Well, it's okay. They are possible, but somewhat intuitive and very geometric. But afterwards, Hamilton of Hamiltonian or quaternion, he proposed an algebraic formal definition of complex number by using ordered pair of real numbers. Z, complex one, is x, y, real numbers. Oh, this is very natural for all of you living in the modern time. But at that time, it was very surprising. And the definition is not this expression, but the definition of addition, multiplication, subtraction, and division. That arithmetic is very important. That is the definition. So addition is defined in this way: x1, y1, x2, y2, x1 plus x2, y1, y2. It's okay, very natural. And actually, it is the same as the definition of real number, two-dimensional real number addition. Next, multiplication, x1, y1, x2, y2 is x1, x2 minus y1, y2, x1, y2 plus y1, x2. Yes, this is also very natural for us this time, these days. But it is very curious in comparison with the real multiplication. There are several definitions, but when we consider inner product calculation, we may take this definition to maintain the dimension, two-dimension, then two-dimension output, x1, x2, y1, y2. This is also very natural. But in the complex case, it is not. very, very well, strange way. But this is the definition made by Hamilton. And once we get this one, then we can also obtain the inverse and also the norm or length of the complex number. Then the complex number is defined algebraically, very strictly. Well, in these years, or almost 100 years ago, we have another definition, which is equivalent to the algebraic one. 2 by 2 real matrix representation. If we consider a multiplication of complex number C, A plus IB, and Z, X plus IY, it is a type of C linear transformation, which is defined as CZ is AX minus BY, I BX plus AY. Yeah, it is also very natural. And if we identify C with R2, two dimensions, in this way, X plus IY, we introduce this representation vector or matrix. Then the transform is expressed in this way, then we get this matrix, 2 by 2 matrix. And well, normally 2 by 2 matrix has 4 parameters, as you know, A, B, C, D. We have 4 parameters. But in this case, we have only 2, A and B. So the number of the parameter is reduced when compared from the with the normal matrix, 2 by 2 matrix. Well, then, by using this notation or definition, the meaning of the complex number is very clear. A minus B, BA, it means a rotation of angle theta and also amplitude, amplification or attenuation. And that's all. This is the meaning of a complex number. Then, what happens in neural networks? Well, the neural network using complex number has a merit in the following meaning. In the feed-forward network, again, the brain feature, well, the most specific feature in brain is the imagination. You imagined where the landmine is. And some people are successful, some people are not. Well, if you hear only a part of instruction, for example, please do this one, you are told, then you learn the whole, not only the explicitly represented instruction, but also something related to the instruction. You will get it. So this is the generalization ability, and it is very useful in solving ill-posed problems. Well, again, we have the network, two input signals, two output signals, and we want to optimize these 4 weights in the neural network. Well, this is the input point, input teacher signal, and output teacher signal in 2 dimensions. Then we apply the supervised learning process. And we often experience well, we determine these parameters. We often experience this solution of the learning. Okay, x in is transformed to x out here. But this point is also transformed to here, this one to here, this one to here, this one to here. So the output makes a single line. So the dimension is reduced in the output, or we experience the degeneration, the reduction of rank. This type of solution is often useless. But why it happens? Well, in this case, the degree of freedom is too large. We have only one teacher signals, one pair of teacher signals. If we can reduce the degree in an appropriate way, then we can obtain a better solution. Okay, we take the same situation, but in a complex domain. One complex number input, complex output, then what happens? The output is determined very uniquely. This point should be rotated this way, and the amplitude is reduced this way. And that's all. This is the unique solution. Of course, we may have 2n pi redundancy, but it's okay, no problem. So we have only two parameters. Then the learning result is uniquely determined. And this solution includes only the phase rotation and the amplitude amplification or attenuation. This is the elementary function made by a neuron. And this result is very good to be used in wave-related information. We often use exponential j omega t or exponential jkr to represent waves. This type of solution is suitable for wave type information processing. It's the generalization property is familiar with the wave phenomenon. And it is very important in general physics because, well, the amplitude is directly related to the energy of the wave, and the phase is directly related to time or position. So if we apply a neural network in, for example, electromagnetic wave applications, then we should use this type of neural network, the complex valued one. That is, the complex neural networks are the physics incorporated neural networks. Neural network is not a black box. And they can realize a good generalization suitable for wave-related phenomena. Okay, we check an example in the radar system I mentioned, INSAR, Interferometric Synthetic Aperture Radar. This is the situation of observation. Interferometric synthetic aperture radar, INSAR, generates interferograms that reflect land shape. Well, this is the Earth. And this is a satellite. And it transmits electromagnetic wave to observe this point on the Earth. This point scatters the wave, and the satellite observes the scattered wave. This is another satellite, or another time when this satellite comes again very near to the previous point. And we make an interferogram by subtracting the phase information from this phase information. And we get this type of interferogram. And in this image, this complicated curve, we have many curves, show the equi-height curves. So it is a contour of the geography. But it is expressed by the phase, sorry, the small character, minus pi to pi as the phase value. So the phase value is wrapped within minus pi to plus pi. It's a problem. We cannot, the phase doesn't say directly the height. And we need to unwrap this phase. Unwrap means we unfold this minus pi to pi folded information to minus pi to plus 2 pi, 3 pi, 4 pi, and so on. This process is called unwrapping, phase unwrapping. And we obtain the digital elevation model, DEM. We want to do that. This is the DEM we expect. But we have a big problem in this process. Well, that is the phase singular point. Well, this is the pixel coordinate, and we have 4 pixels here, which is represented in 3 dimensions. This is the x-axis, y-axis, and the height shows the phase value. If we determine this place as 0 height, for example, as a reference, then we can height here by walking through this way, walking this way, walking this way. And then we come to here. But the height is different when we walk around this point. Why it happens? Well, it's okay when we think the height, well, the phase value is the data. This is 2 pi phase data, and this is 0 phase data. Then 2 pi radian is equivalent to 0 radian. There is no inconsistency. It's okay. But when we assume the phase value is height, then we have a big problem or a big cliff here. We cannot determine the height then. And a very traditional way to solve this problem is the branch cut method. If we have a negative one that has a downward slope, we want to find a positive one singular point that shows upward slope. And then we connect these 2 points to make a cliff here. Then we can determine the height. If we start from here, we can determine the height here, 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 here. And we can get back to the starting point without any inconsistency. Probably you can imagine the complex analysis that includes 2 different types of residue. Then there is no inconsistency. So it's okay. It works. Anyway, we make these, this line is called branch cut. And we make these branch cut because this image, the image includes many, many singular points. We have many, many branch cuts. And we determine the height by avoiding crossing this line. But this cliff is very artificial or artifact. So it should be very small in its number, or it should be very short in its accumulation of the length. So, well, this is the height map digital elevation model. We see some very strange lines. Can you see? This is artifact, not the real geography. So we have to minimize the length of this branch cut. But it is a very hard problem in general because it is a combinatorial problem. We have to choose one negative and one positive. And which combination is better? This one, this one, this one, this one. We have to check all of them. Then, when the number of the singular points grows, then the calculation cost explodes. Big problem. This is an actual data again, but it shows Mount Fuji. I hope some of you know Mount Fuji shape. It is a mountain in Japan, the highest one, but lower than the Taiwan mountain. Okay, this is the summit, top of Mount Fuji. And it has a very wide skirt region. Again, the contour curves show the equi-height positions. And then we can imagine, probably I expect that you can imagine what the shape is or how the shape is. Okay, this is the top, and yes, this is very steep here, and the steepness decreases, so the shape is, we can imagine it. But the computer cannot imagine the shape because of the singular points. Many, many singular points we have in this image. Actually, this red circle shows the positive singular point. And green crosses show the negative ones. And they are located at the end of contour. Here, 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 here. Many, 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 but they are always at the end of contour. But it is very funny, strange. Contour should not be end. It should circle without any end. But in the real data, we find many ends and many singular points in this way. Then we developed a filter to compensate or remove the singular points. The name is complex Markov random field neural network. Well, Markov random field model is very widely used model in statistics and neural networks. And this is a complex version, complex valued version of the normal Markov random field model. And we can define an energy in this model, and we make a dynamics of neural network to reduce the energy. And the most simplest case is this one. We find that we just take the correlation between the singular unit, well, singular point making pixels, these 4 pixels, singular unit, and the surrounding pixels, surrounding ones, Q. We calculate the correlation between this one and this one, and then we store the value and apply the value to rewrite these 4 pixel values. This is the most simple case, and we apply it. When we find a singular point here, then we gather the statistical information around this singular point by applying this window, local window, to calculate the correlation, and the local window goes around, and then we apply the result of the correlation value to generate these 4 pixels, or overwrite the value, because it is distorted. It is not real geographical data. And then we remove the distortion and remove the singular point. And actually, what happens is not this one, but the singular point moves a little by 1 pixel to another location. But anyway, we can make it disappear. Okay, this is the data showing Mount Fuji, and this is the summit. This is raw data, raw phase image, equivalent to the grayscale one we saw. And if we apply an averaging, very normal conventional filter, then the white noise is completely removed. It's good. This is the raw data, and normal averaging process filter. It's good. But at the same time, we see the smearing removal of the fringes. The fringe is the signal showing the height. But here, the fringe disappears. Then we cannot determine the height. Another filter, Goldstein-Werner filter. This is a filter very widely used presently in real processing in this field. Well, the result is much better than the normal traditional ones. We can see clearer fringes here. It is much better. But by applying the complex valued Markov random field model based filter, then we find this way. We can see more, much clearer ones fringes. This is the conventional one. This is the very traditional one. And this is the raw data. And even in the raw data, we cannot see the fringes explicitly, but we can imagine. Here we should have some fringes we can imagine. And the new filter realizes this process, realizes this imagination process. The fringe is made based on the raw data. So this process realizes what our brain does. Okay. More microscopically, we can observe this process. Well, we zoom in to a part of the raw data here. And in this view graph, a black point shows -1, negative singular point. And white one shows a positive one. And we have many singular points. And the proposed filter is an iterative process. We apply it 1, 2, 3, 4 times. Then we check the changes in the number of the singular points and also the location of the point. Okay, this is the raw data. And once we apply the filtering process over this image, then this is the result. Most of the singular points disappeared. In particular, these neighboring ones disappears. And please pay attention to these pairs. Okay, this is the first time, and second time, third time, fourth time, they disappear almost completely. We go back, go back, go back to the raw data. And then again, this is the first time, second time. And we can see the points getting closer and disappear. The singular points find their counterparts by themselves. We don't need to assign. You should be paired with this one. We don't need it. They know by themselves, and they approach to each other. Then we are free from the combinatorial problem, the computational cost explosion problem. This way, the singular point disappears. And well, in this case, we have 3 remaining singular points. And it is okay. Well, they are called isolated singular points. And it's okay. It often shows real cliffs. We have a cliff between this one and this one, or this one and this one, or sometimes this one and out of this image. Okay, this is the digital elevation model obtained by using the conventional averaging process and the new ones. Well, if you know the shape of Mount Fuji, this one is very nice. This one is not so. And in this Mount Fuji case, we have a solution. We have the real data of height. And we can calculate the signal to noise ratio. In this case, the signal is the height. the peak and the bottom. And the noise is the error at every pixel. And then this is the conventional one, and this is the proposed one. And mean square error in height is shown here. The error is very much reduced. And the SN ratio, the error, well, the signal, the height, squared height over the error, squared error, the SN ratio is, gets much higher. And peak squared error value is also reduced, and the SN ratio also grows. It is very successful. But some people may say that, okay, yeah, it works. But when you make a program, software, probably you made it in such a way that z is x point y. Complex number is constructed as two-dimensional real numbers. Then we may get the same result even if we apply a double-dimensional neural network. But actually, no. Well, this is an example. Well, this is the raw data. This is the raw data showing the phase and the singular points here. Well, we have many small white points and black points. I hope you can see many. And if we apply the complex valued Markov random field based filter, then the phase information is almost the same. It seems almost the same. And the number of the singular points reduced very drastically. And this one shows the double-dimensional real-valued ones. We noted real and imaginary type Markov random filter. Well, the number of the singular points reduces again to a great extent. And the phase value seems very similar to the original one and also the complex valued one. But, well, in a precise examination, it is not. Well, this is the histogram of the original phase value. This is minus pi. Here we have plus pi. This is the phase value, and histogram is shown here in the vertical axis. The number of the pixels, minus pi pixel number, some thousand, and so on. Here, this distribution is the original one. And the CMRF result shows almost the same distribution. But real and imaginary process result shows very different distributions. The number depends on the axis phase value. Well, we have peaks at 0 radian and minus pi over 2, half pi radian minus pi, and so on. In this way, it is very different. Okay, then the result shows a type of generalization properties. And we found that the complex valued neural networks show a very nice generalization characteristic. Okay, time's up. In summary, the feature most specific to complex numbers is the phase rotation, as well as the amplitude, amplification or attenuation in its multiplication process. The complex valued neural networks are suitable for wave-related computation. And I didn't say much, but it is a type of sparsity. Sparsity is very important in this kind of learning process to obtain a good generalization. And the field, well, the wave-related field includes many electronic phenomena, such as communications using electromagnetic wave, quantum devices, coherent one, and other things. Actually, some people apply this one to traffic signal control because it also includes the periodic dynamics. And complex valued neural networks are highly useful in interferometric imaging radar systems. Okay, that's all today. Thank you very much for your kind attention.
Any questions? Yes.
Professor, do you expect this process can be applied to process?
Sorry again, please.
Do you expect this process can be applied to CUDA?
General purpose graphical processing. Well, yes, yes, it's possible. It is a type of neural network, and the number representation is a little different. So then we can utilize GPU. It is the same case as the normal neural networks.
Very good question. Any question? Yes.
Okay, thank you. First, I wish to thank our professor to deliver these types of talk. I was really interested with that. Maybe I might have one question. So the question is, in your presentation, maybe page 9, in artificial neural network, you were focusing on only forward approach. But can you use maybe back propagation? In the neural network, you are focusing on this forward. What about that approach? Thank you.
Well, in this explanation, I assumed back propagation and the feed-forward neural network. This is an example. And, sorry, your question is?
Yeah, this neural network is feed-forward, right?
Yes.
But can you apply this backward propagation?
Yes, yes. Yes, we have actually some versions of back propagation in the complex domain. And details are given in the book or papers. And well, in many cases, teacher signal back propagation is very useful in this purpose of dealing with coherent information instead of error back propagation. Well, we may talk details later.
Okay, and the detailed information will include this book. So I will ask our librarian to push some books from Professor, and you can borrow the books from our library. Okay, yes.
about like you use bubbles and then image processing your neural network. Have you ever tried in another field, stuff like power system or another field? Not then, only in image.
Pulse neural networks?
Yes. Did you try your research on that?
Well, we are not so active in pulse neural networks or spike neural network. Well, but it is highly related to this type of neural networks because the position of the pulses in time domain is very almost equivalent to the phase in the complex domain.
You can show like this way, right? So
yeah.
that's why maybe you tested or not. So I'm very interested in your.
Not tested, but yeah, your suggestion is right. I think so.
I have one question.
Thank you.
For the echo signals, maybe have the multi-pass phenomenon. So what do you think about with the multi-pass your systems for the evaluations and analysis? Thank you.
Thank you. Yes. Well, in communications, we have many types of multipath situations, and the complex valued neural networks is very effective in solving complicated multipath situations or fading situations. Well, I think I have PowerPoint here, but you can't. Because in that case, we use the ability of prediction of the neural network. And well, we observe the received data for a while, and then we predict the next interference situation, and we compensate the received data with the data predicted by the neural network. It is very effective.
Thank you, Akira Himoshi-sensei. And we are thoroughly enjoy and appreciate your talk at Taipei Tech. You have made a great impact for the IEEE GISS, our distinguished lecture program. If you have any further question, you are welcome to write an email to
Yes, please.
I think we will be happy to answer your question. Finally, we will like to give you a certificate of appreciation as please our Dean will represent NTUT to award this certification of application to you.
My great pleasure.
So
you.
finally, please join me to give
Thank you.
You want a group picture?
Group picture, yes.
Okay. Together, can we?
Yes.
Yeah.
First.
Also.
Thank you very much. Thank you very much.
Thank you very much. Thank you for that great talk. Awesome.
Could all of you, including professors and students, which would like to join our team and take a group picture, you are welcome to come to the stage here.
团体照。
团体照。
来。那个
You will get an extra bonus, extra credit.
Yes. He's a PhD student of the Dean Huang. Yeah.
Thank you, Professor.
Rose.
Okay. Okay, thank you very much.
Okay, thank you, thank you.
Okay, thank you very much. Thank you very much. Yeah, thank you again. Thank you very much.
TV and register one free account, and you can have the video free for free. Okay. Thank you for joining me.